So my name is Vishwa, and I'm an application engineer at Computational Enterprise Simulations. We are the channel partners of MathWorks in the Middle East. So I'll be the presenter for today's webinar on developing UAV models using the appropriate level of fidelity. So today in this, we will look at how to select appropriate model fidelity level for modeling a UAV platform. Also, we will look at different levels of fidelity modeling by considering examples and understanding the trade-offs between them. So our today's agenda would be, first we will start with a small introduction to mathematical modeling. Then we'll understand what is meant by model fidelity. Then I'll explain the design cycle of a UAV, unmanned aerial vehicle. Then we'll look at different modeling methods. And finally, I will show you 3 demos. Actually, it will be 4 demos in MATLAB. So one will be like low fidelity modeling, medium fidelity modeling, and the high fidelity modeling. We'll see the differences and the trade-offs between them. So before we start, we'll try to understand what mathematical modeling is. So what is mathematical modeling? Well, when I was putting together this presentation, I did some searching online and I found that almost everyone talks about mathematical modeling slightly differently. So the definition would depend on who you ask and what their background is. So for example, when you talk to an engineer, it's different. For mathematician, it's different, and biologist and so forth. So when you listen to everyone and when you boil everything down and when you understand what this is, there's a common ground in almost everyone's definition, and that is the use of mathematical language to describe a system or a process. So mathematical modeling is a language, like it's a we use this we use mathematical language to describe a system or a process. So the mathematical model always accepts inputs, and based on those, it calculates the outputs. So if you look at there's an example here, lift on aircraft wing. So when you look at this, so we are trying to describe this lift on aircraft wing using an empirical parametric equation, where the inputs to this equation would be aircraft weight, speed, and angle of attack. So now we understand what mathematical modeling is. So why do we have to use it? Like, what are the uses? So for the first one comes as forecast system behavior. So you want to predict and gain insight into a system behavior for various what if scenarios. The second one is to optimize system behavior. So you can identify parameters that optimize system performance. And the third would be to design a control system. So you can develop the model to represent the plant while you're working on your control system design. So now we understand what is mathematical modeling is. So this mathematical model can be classified based on the amount of information that is used to model. And it is classified as high fidelity models and low fidelity models. So when we look at what is high fidelity model is, so the high fidelity model is a detailed model. So it incorporates many things about the model, and they are modeled with less assumptions. So they almost mimic the real system of the process. If we consider an example of a UAV model, a high fidelity model incorporates modeling all the forces, moments, wind, environment effects, and sensors in detail. So on the other hand, the low fidelity model is an approximate model. So this model will be ideal model for a particular work or particular scenario. and it has a lot of assumptions in it. So it's a very simple model, and it has a lot of assumptions. Yeah. So this is low fidelity model. So based on the amount of information that is used to model, we are classifying as different level of fidelities. So we understand the mathematical modeling and the model fidelity. So now we can use this terminology to understand UAV design cycle. So here in the picture, it represents a UAV design cycle. From the picture, we can see how the fidelity of the model is changing with the amount of information available. And we can see there is an incremental increase in the UAV plant model fidelity through the design process. An approximate model, if you see in the lower side, an approximate model is used in for the initial parameter tuning, and the model fidelity is increased as algorithms are refined. So the unmanned aerial vehicle design cycle provides incremental better access to UAV's characteristics as the design progresses. By increasing its fidelity, this information can be used to continuously evolve a plant model through a model-based design. You can see towards the end of the design cycle, we will have enough information to develop a high fidelity plant. To accurately model the UAV, a high fidelity model incorporates all forces, moments, wind, environmental effects, and sensors in detail as mentioned before. However, this level of information may be unavailable to the designer early in the design process, right? So in the starting of the design process, we might not be available all this data. So, and also to build such a complex model, it can take several flight and wind tunnel tests to create enough detailed aerodynamic coefficients to compute all forces and moments that affect the UAV. These factors can potentially block guidance algorithm design until the end of the design process, when a more realistic estimation of UAV dynamics is obtained. So we can concurrently design a guidance algorithm sooner. A UAV algorithm designer can start with a low fidelity model, like you can see here, and evolve their plant model as when additional data becomes available. So when you have like data like preliminary aerodynamics, like and motor selection, design specifications, when you have this, you can go to mid-level. And when you know a detail about the model, then you can go to the high fidelity. Okay. And designing a guidance algorithm only using a low fidelity model can pose a risk without controller or aerodynamic constraints. An optimistic guidance technique can fail a real UAV with slower aircraft dynamics. So in this webinar, we will highlight an alternative approach. You progress from a low fidelity guidance block to a medium and then to high fidelity by progressively adding layers of controls and dynamics to the simulation. So when we talk about modeling the UAV platform, the recommendation is to select the appropriate model fidelity level based on the task involved in your project. So what do I mean by this? So if you're building a new UAV platform, like completely new, you might need to provide a detailed model of your UAV. In other words, a high fidelity model of a UAV. But if you're really focused on the autonomy applications for UAV, maybe it's sufficient to start with an approximate model. So there are trade-offs. As the more detailed the model is, there is more processing that can take more resources in terms of simulation time. And when you use an approximate model, you're able to execute it quickly, but you will not include the detailed UAV components. So if you're building a new UAV platform, you will be creating high fidelity models. So for this, you can use physical modeling, and this is a method that supports building high fidelity models. So We do this by connecting physical components rather than equations through the add-ons. So this physical modeling, you can do it using Simscape products. You can build these models with components such as joints, bodies, motors, and other physical components. So I will show you an example about this physical modeling, okay, in the demos. So you'll understand more about it. And also one more capability that a Simscape can give is you can include import CAD models to start as a baseline to build up your UAV. So you can do this physical modeling with an add-on called Simscape products. So the second one is the aerodynamic. We'll be using equations of motion. So for this, we will be using the aerospace toolbox. Aerospace toolbox also provides some methods to build high fidelity models by using the 6DOF or 3DOF equations of motion blocks. This can determine the UAV position, velocity, altitude, and other related values. So if you want to use a little slightly approximate mid fidelity model, even that is also available. And for that, we will be using point mass block. Okay, this block represents the equations of motion for a point mass, and it also includes environmental effects for you to model, such as wind and atmospheric effects. We will see more of these in next slides and also in the demos. So the last one is approximate UAV guidance model, and this is an approximate model of UAV. So these blocks are available in UAV toolbox as guidance models for simulating an approximate autopilot controller, as well as for the dynamics of the UAV. And this is available as fixed wing. You can see here the fixed wing guidance or multi-rotor guidance models. So you can set the parameters for the UAV, and you will be using and you can get started right away with the simulation and focus on the autonomous algorithms than on the uh, kinematics of the model or dynamics of the model. So let me introduce this one. This is the UAV toolbox. Okay, we can quickly using this we can quickly simulate UAV using fixed or multi-rotor guidance models. It has tools for designing, simulating, testing, and developing unmanned aerial vehicles and drone applications like autonomous flight algorithms, UAV missions, and flight controllers. With this toolbox, you can simulate UAV dynamics prior to availability of detailed plant model. Perform high-speed simulations with approximated UAV models like fixed wing and multi-rotor models. You can perform initial parameter tuning in different test scenarios. So in UAV toolbox, if you want, when we are going from low level to medium level fidelity models, we can use fixed wing UAV point mass block available in UAV toolbox, and also this block is available in aerospace toolbox. The block only requires lift, drag, and thrust forces as inputs, which are easier to approximate at an early design stage than detailed forces and moments of an aircraft. So to go from medium to high level high fidelity model, so the high fidelity plant incorporates all forces and moments to a 6 DOF block. So this is a 6 DOF block, and it takes inputs as force and moments, and adds on board sensors and model actuator dynamics for the UAV. Unlike the mid fidelity plant, the high fidelity version does not take altitude inputs directly. Instead, an inner loop controller is added to the control altitude Additionally, a yaw compensation loop balances the non-zero slips. Okay, the model reuses the outer loop controller design for the medium fidelity model. And to validate that, the medium fidelity model provided useful intermediate information, and we use the response for the high fidelity model. Let me show like all these low, medium, and high fidelity models in MATLAB. So let's switch to MATLAB. So here I'm using MATLAB R2022B. So the example which I'm using is already available with the toolbox, UAV toolbox, and it'll be in this location, MATLAB example. So this is an example which comes shipped with the uh, toolbox. So let me open the low fidelity model. So this is the low fidelity and this is running. So the low fidelity model, like so here we have the inputs, step control inputs. When we go into this, so this is the input. So here we are giving air step airspeed. So here we are giving three inputs. So this is a bus connector, and we are clubbing all these three inputs and sending it as a single output. So here we are giving input as height, airspeed, and roll angle. Okay. And here in this case, only the airspeed is like a step response, and both of them are height and roll are like constant inputs. And in other blocks, two are kept constant, and the other one is like a step input. So this is the input here. Okay. And this is a step response model. And here we have the models. So here we have low fidelity, mid, and high. Right now, only the low fidelity is active. So let's open this and see what is there inside it. So in this, we are using a fixed wing UAV guidance model. So this is the block that I was referring to. And it has two inputs. One is the control and the other is the environment. So for the control, we have seen that we are giving height, roll, and what do we have here? So we're giving height, airspeed, and roll angle. Those three are entering here from this signal to control. And the environment we are giving north wind, wind north, wind east, wind down, and gravity. So these are the six, like 4, 5, 6, 7 inputs that we're giving to this block. Okay, and let's see what this block is. So double click on it. And here you can see when you open this block, you can either select fixed wing or multi-rotor guidance block. And here you have initial states. You can give the initial states, then you have configuration and input output bus names. To know more about the block, you can first read here about the block, or if you want to know more about the block, let's go to the help button there. And here we get the help. So the name of the block is guidance model, and it is a reduced order model for UAV. And this block is available in UAV toolbox algorithms. And the description about the block is, so this block actually uh, is a block represents a small unmanned aerial vehicle guidance model that eliminates the estimates the UAV state based on control and environmental inputs. So we have two inputs, that is control and environmental inputs. So what this model is, the model approximates the behavior of a closed loop system consisting of an autopilot controller and a fixed wing or multi-rotor kinematic model for 3D motion. So the inputs, I told you that we have control and environment. So the control, there are two models, right? One is multi-rotor UAV or a fixed wing UAV. For the fixed wing, what we're using, we have three inputs, that is height, airspeed, and roll angle. But when you're selecting a multi-rotor UAV, you should give roll angle, pitch angle, yaw angle, and also thrust. So you can see here it's all written. Roll angle is in radians, angles are in radians, and yaw angle is in radians per second, yaw rate, and vertical thrust is in newtons. So same way, if you're looking at the environment, even this is an input. So for the fixed wing, now we are using fixed wing. For this, we have to give wind north, wind east, wind down, and gravity. And if you're considering a multi-rotor UAV, so you only give gravity as the input, and that should be in meters per second square. So your output, what you when you give these inputs, what you can expect as output. So as output, if it is a multi-rotor UAV, you can get world position in meters, world velocity in meters per second, or Euler's ZY X, so Euler angles in radians, and body angular rate and thrust. So if you're using a fixed wing UAV, output will be position in the north direction, position in the east direction, height above the ground, airspeed relative to the wind, angle between ground velocity and north direction, and so on, all of these things. And the parameters are listed here. And the reference for this model you can find in these references. So this is a UAV guidance model. So these are the inputs. So these are the outputs. Okay. So if we go out, so the outputs are mm, we we have like many outputs, but out of all of them, we are interested in looking at height, airspeed, and roll angle. Okay, and these when I simulate, these are going to the workspace. So you can see them here in the workspace. Here, let me run the model. So here we can see SM roll, SM height, and this. So what exactly we are looking with this low fidelity? So we're trying to see with the low fidelity, we are first estimating how fast the UAV can realistically respond to help tune high level parameters. So here we are actually looking at this height. I can plot these and show you. So height, if I go to plots here, so after you get the outputs, it's very easy to plot. So you go to plots here and you select your output, and automatically you'll get what plots you can make with this data, and it'll suggest you those. So here I can make only one plot. So when I click on this, I can see. So this is the airspeed. Okay, airspeed response. And here when we look at height, so height is constant, and roll angle, roll angle is constant. So this is a low fidelity model. Okay, so now let's look at the medium fidelity model. As the UAV design progresses, the lift and drag coefficients will become available. So the motor for the aircraft is selected by the user by that time, which defines the thrust curves to test the validity of the guidance algorithm against this new information. So we can add more information to it. So let me open the medium fidelity model. So let me click on this. So let's wait for it to open. So to design a medium fidelity model, the model needs only preliminary aerodynamic coefficients like thrust curve and response time specifications. To model a medium level UAV, you can use a fixed wing point mass block. So there we used guidance model. Here we'll be using fixed wing point mass block, and the block only requires lift, drag, and thrust force inputs, which are much easier to approximate at the early design stage. So here you see we have the outputs. So this model is running both low fidelity and medium fidelity and low fidelity model, and we can see the comparison between them. So let me open the graphs. So this is figure 1. So here we can see this is a roll response. So both of them are almost same. And here we are seeing the height response. So the medium fidelity is not low and medium are like having difference. That is because we added like more data to the model. So the model is comparative to the low fidelity. The medium fidelity has the response is different. So let me open the model here now. So in this case, you can see this medium fidelity model. So when I open this, now this is active. So here we have inputs. So we have inputs. This is the controls that we're giving to the model. And inside this model, we have an outer loop autopilot. And then we have UAV plant dynamics. And also we have here environment. So environment in this case is a study environment. Let me first open this block, and you can see these are the environment inputs to the model. And here commands are not directly going from the step response, but you have an outer loop autopilot. So let's open this. And here you can see we have two controllers. One is for altitude controller. You have a PI controller for this, and airspeed controller. You have PID controller. So these are the inputs that are going as commands. So they are not directly going from the step response, but you have a loop controller before the model plant. So if you look at the plant, so here we have the plant inside this vehicle dynamics. So before we go, you see here we're giving commands and environment to the dynamics, but you see we are not directly giving this command and environment values to the block. So here we are using, for the medium fidelity, we are using fixed wing UAV point mass. And you can see these are the inputs required. So we are taking the command and environment, and we're calculating forces that are required for the block. And these are again, the outputs from these are autopilot states. So we are using them as a feedback to the calculated force. And also we are using this autopilot values as feedback for the controller. You see, autopilot is used as for the controller also. So when you compare with the old model, we had one single block. Okay, and it was taking only commands and environment, but you can see the complexity. We have added few more layers to this um, to to make it more complex. So let me run another model in the low fidelity itself. So for the medium fidelity. So here we are in the medium fidelity. I'm trying to run this simulate path follower. So here we are trying to simulate a path follower. So what we saw before is we were giving step response, height, age, speed, and roll angle directly to the model. Now here it is little more complex. So in this, we are trying to see how the model is going in the path which we are defining. So we're using a UAV waypoint follower. Okay. And we have some more blocks here to calculate height, airspeed, and roll angle. And these are fed to the model. And also they have a steady state. So, and when we run this, you can see that the block, the output of here, this is actual, already it is run. So I'll open this. So we're seeing how the model is following the path, and it is following, it is tracing the path properly. So it's good. So this model is actually tuned to trace the path. So with this, we are seeing tuning waypoint follower for a fixed wing UAV. Next, what we have is we have a high fidelity model. So when we're moving from a high fidelity model, so when we use this medium fidelity model to test a path follower design using simple aircraft parameters available in the early design state. Sorry. However, it is important to continue adding more fidelity. So here we have a high fidelity model. You can see the difference now. So in this, we will have actuator dynamics, sensors, a complex model. We use 6 DOF block. So let me, okay. So this is running, this is now we are running the model and we're trying to compare the high fidelity with medium fidelity. We'll see the response and then you can see here. So this is the high fidelity model for the roll response. And you see this is a medium fidelity. So we are adding more things to the model and the model is responding a little different compared to the previous models. You can see here height response is also a little different. And then you'll have, so when we have roll response, height response, and then we have, so this is a speed response. So actually it is running twice. So no, we'll have one more graph. After that, we'll look into the model, how the model is. So this is the final plot. Okay. So let me close this graphs. So here is here now we have activated high level fidelity model. So let's look and go into this and understand. So here, if you see, it has more blocks compared to the previous model. Here we have a sensor block. Here you can see autopilot, and here you have plant model. So we'll open plant model first. So when we look at the plant model, inside the plant model, we have unmanned airplane plant model and sensor model. Both of them are there. When we look at the plant model, this UAV model, we have actuators. See, before we didn't have actuator models. You have actuator models in this case, and you have UAV dynamics. So, and UAV dynamics, we have here, we have 6 DOF equation block. So for this, inputs will be force and moment. And these force and moments are calculated with some inputs. Okay. And we have actuator model, weather model, and assemble GPS and state data. So this is the aeroplane plant model. And here we have sensor model. So even sensors are a model, noise and sampling model. So this is a plant model. And here when you see the autopilot, before we had only outer loop autopilot. Here we also have inner loop autopilot. And then we have sensor module. So inside this, we have sensor conditioning, position filter, and so on. So this is the high fidelity model. So you can see the difference, low, medium, and high fidelity. You can see the complexity of it. Now uh, let's look at another high fidelity model. So we have seen right now we have seen models with equations like high fidelity with equation. As I told you, we in Simulink we also have another module called Simscape. So with this we can model navigation. We can do physical modeling. See the model navigates. I'll show you an example of this. A drone model, quadcopter drone model in Simscape. So this model actually navigates a path to deliver a package and continues the following and contains the following components in it. So in this, we will have electrical motor and battery, and we'll have the chassis like you can see here, the model like this. So we'll have a 3D files of this chassis and we'll assemble them. And you'll have PID controllers, and you'll have path following and speed controllers. And previously we were giving weather data into the models, right? Here we'll have live data almost like Python queries from a weather database, wind gust profiles, and profitability analysis in MATLAB app. So let me open the model in MATLAB. So let me go back. Uh, so this is a location of the model. So, so this is the physical model of a quadcopter. Okay. So let me run this before I go into the model and show you all in detail. So when you run a model, when you build a model in Simscape and when you run it, you're gonna visualize the results in a graphical way. So this is called Mechanics Explorer, and this is how you're gonna view the results in when you build using Simscape. And you can see here how we can see the stability of the quadcopter. And this yellow line is a path that the quadcopter is tracing, and the block down underneath the quadcopter is what is a package. So that is it's trying to deliver like to another place. So now it's going and it's see that is the target where it has to drop the block. So it's going to drop there and again trace the same path and go back. Okay. So let me stop it here now. So you can see here. No, let's explore. Let me stop it completely. Okay, let's explore the model now. So here you can see. So this is the plant. This is the quadcopter. Before we had six to off and everything. Now it's a little different. So here we have a quadcopter. Here we have a controller. Okay, and this is the reference. And here we have environment. Okay, when you go into the commands, you can see different controllers here. So here I'll be opening the quadcopter model. So here we can see the quadcopter model here. So here we have electrical components related to the quadcopter, and here we have the mechanical components. And here we are showing the ground and the reference frames. So first I'll open the electrical model. So let's look inside it. So here you can see the battery model. So this is the battery model, and you're giving the heat, temperature, and everything to this. So this is the this is a physical model. So you're not writing equations, nor you're describing it. So you will in this, when you use Simscape, you use blocks. So this is a motor. So you use it as a block and you connect them as physical connections. So here, this is the motors. These are 1, 2, 3, 4 motors. And these are the blocks. And you have a small controller here for every motor. And this is the battery. So this is all the electrical part. And you can see the outputs P1, P2, P3, P4, and these are connected to the propellers. So propellers are physical components, mechanical components. So when I open the propeller, here you can see some blocks here. So these blocks actually have the CAD model. So when I click on this, you can see the cap here. And here you have the propeller. So you can see these are bought as step files. So these are the, and you connect them with the frames, like you give the transformations and connections between them. So here we are connecting this propeller to a housing. So this is a housing, okay, using with revolute joint. And here you can see there's a Simscape block. So this is creating the thrust and drag based on the inputs from the motor. So, and also you have, and this is propeller is connected to the body. The same way the body has different components and they're all connected. And here we have the load. So this load, so this is the load, all the components for the package. So you can see the block and different logo. Then this is connected to the ground. Okay. So this is the ground. We describe the ground with different that position that we have made markings on the ground. So we can define those. And here we have, so this is a physical representation of the quadcopter. So what, so in this presentation, like we have seen different fidelity modelings. So we have seen I've shown you physical modeling. I've shown you equations of motion, and also you have seen UAV guidance models. So, so I end the presentation here.